Welcome back. Part 2 of Wednesday morning. Okay. Let's talk about some TCP windows. So we talked a little bit about how that number is established at the beginning session, right? So when we are advertising, keep this in mind, when we're advertising a window in a packet, okay, so I'm a SYN, I send off my SYN to the server, and I'm advertising that number. That's a receive window, okay? So there's basically two windows that we'll talk about. There's receive window and congestion window, okay? The one that you see advertised in your packets is the receive window. The sender of that packet is saying, don't send me any more than this amount of data. That's my receive buffer at once, okay? So going back to Hansung's analogy that I really liked, you have your pipe, and I want to fill that pipe with water. That's my goal if I have a big data transfer. The server can send water over to me in a bucket, but it can only send as much as I can receive into one bucket at once. Otherwise, what happens? If I got a thimble-sized bucket, and he's got a big 5-gallon paint pail, and he shoves that down the pipe, and I'm there with my thimble going, ah, God, ah, right? Right? So that server is limited by my receive window. Okay, now in a perfect world, in a perfect world, the network has infinite capacity, right? The receiver can receive at infinite capacity. We have this huge bucket that will never fill. The sender can send at infinite capacity. There's no limits. Our sending bucket, the amount of, okay, I've got a bunch of water to send. Our bucket's so big, it's a swimming pool. The pipe to carry that is swimming pool size, and it's going into a massive swimming pool. That's in a perfect world. The reality. Boom, as in, yeah, rock and roll. In reality, the network has limitations. Let's just be honest, right? We're limited by bandwidth, we're limited by latency, we're limited by things like packet loss, congestion, errors, discards, buffers along the way that can get overwhelmed. We're limited by translating between 10 gig to 1 gig. We're limited, we have lots of limitations from a network perspective. So end to end, I don't have this massive swimming pool carrier between these two endpoints, especially if they're any distance apart from each other, unless they're on the same 10 gig, 40 gig, 100 gig switch, and they can make the most use of it if they're just cabled in and right next to each other. But client to server and most of the stuff that we're going to be troubleshooting isn't like that. There's some network in between. I mean, maybe we'll be doing that type of troubleshooting. That's possible. I'm actually going to show you a few examples there. But the reality is that we do have limitations on the network. Another reality is the client has limitations. Okay? I might be able to tell that server, I can only receive, I'm just making up a number, 8K at a time. That's all I can take. Why? I got a bunch of other resources going on. I got other things happening. Maybe I have this receive bucket and the application isn't scooping it out fast enough. Right? So my receive bucket to receive all that water can be a limitation. That's set by the TCP stack. Another reality, the server has limitations or might intentionally limit itself due to network conditions. Let's bring up the idea of congestion window. Now, congestion window can be this nebulous number that no one sees and knows. It's basically the amount of data that server can send at once. How big is the bucket that it can pour data down the pipe to the other side to? How big is that bucket? We're going to talk about it for a little bit, but first I want to make sure we understand the receive window. That's a more clear one to get. All right, let's take a look at the receive window. Just want to walk you through an example here. Receive window. Okay, back here. All right. Now, we missed our handshake, but I'm just going to tell you, these two stations weren't using window scaling. All right? So the number you see is the number you see. What you see is what you get. This window size value is true, it's real. Don't worry about calculated window size at this point. I'm going to remove this column. All right? Okay, so basically what was happening here, let me give you a little bit of a problem statement. One of my clients was backing up a database from one backup server to the other, just moving from a primary server to a backup server. Same switch, gig attached, sitting right next to each other in the same data center, literally. And they were just like moving this data from one machine to the other. Now, originally, they started this backup after everyone was done with their workday. They go home at 5 Pacific time. They start the backup. And by the time East Coast people were coming into work the following morning, think in terms of Pacific time. So the following morning at about 5 a.m., people in the East Coast started coming into work around 8-ish in the morning. That backup was still running by the time people were coming in. So gig attached. It wasn't a ton of data. I don't know. I can't remember the exact details. It must have been, I don't know, 300 gigs, 400 gigs, something like that. I mean, just doing the raw numbers on that, think about it. Even if okay, let's just say an 800 gig database, right? If I have 1 gig interface, and I'm moving stuff at line rate, how long should that really take? 800 gigabytes, divide that by, or multiply that by 8 to get the bit value, or bits to bytes, right? And then divide that number by my link speed. So basically, it shouldn't take a whole lot of time, right? But this thing was taking all night, 8 hours. So what was the first thing that these guys thought to do? Well, 1 gig. We need some 10 gig on this thing. Now, smartly, if that's a word, it isn't, ironically, they first did a packet capture, and we talked about it before they went and completely forklift out that infrastructure, brought in a bunch of 10 gig and snapped everything in. This is just a sample of the trace. The trace was huge, but it does start to show you some of the problem that we have. Now, right here for delta time, I'm just going to come down here real quick. Notice that everything you see so far is sub-millisecond, all right? Eyes are here. Eyes are here. All zeros, zeros, everything's sub-millisecond. We're cranking. We're slamming data. We are just moving. And about here-ish, yeah. Everybody see that? Okay. So we're slamming data. And then we have this 19 milliseconds. Now, 19 milliseconds. Am I going to fuss about 19 milliseconds on the grand scale of things? Am I going to go, oh, man, there's your problem right there? Well, I mean, 19 milliseconds, big deal, right? 19 milliseconds doesn't hurt if we suffer it once. 19 milliseconds hurts if we suffer it thousands of times. Everyone agree? So sometimes it's death by these little delays that'll get you. Sometimes things are 108 full seconds of delay, like the trace file that I showed you before the break. 108 full seconds, whoa, boom, there's my delay, wow, goo. It's clear, right? Application delay. But sometimes it's these little guys that'll bite you. The question is, how often do I suffer them? I'm just going to take that value right there, packet 140, and I'm going to sort my delta time. What this does is it puts all the deltas now, the worst ones, together. I'm at the bottom of the list. So I can see that 19 milliseconds is not something that I only suffer once. I suffer it quite a few times. And I did have this outlier, this 60 millisecond outlier, but this was the server coming back to the client. I mean, at one point it took 60 milliseconds. But most of these delays are these dead acts coming back to the server, okay? These are the empty packets. That's what's taken 32, 25, 20, 19, 19, 19, 19, 19, 19. I do have another one out here. It's another outlier. I can investigate that. But most of them, and this is just a sampled trace file. This is just a very small amount of this trace file. If you took a larger section of it, 500 megs or something like that, you would have seen these 19 milliseconds go on into the sky. So we suffered it. I mean, the grand total of this trace, let me see here. This isn't even a 1 second trace. This is only 800 milliseconds of, 873 milliseconds of the total trace. This was just bam. And this thing went on for hours, right? Okay, so I'm concerned about those little pauses. So come down here one more time. Let me find my little pause. Now, what is it that I was waiting on? Data is coming across. You see my 1514s. That's my Ethernet length. Data is coming, so the server that wants to back itself up and send data over to the other guy, he's sending big packet. Bam, 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 bam. Receiver of that data, every other packet. Thanks, 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 thanks. It's incrementing its sequence number. Excuse me. It's incrementing its acknowledgement number, excuse me. Well, then we get down to this point where we wait. The server has to stop for a second, packet 139, and we have to wait for 140 to come in. That was a 20 millisecond pause. After that, bam, more data. Okay? So let's take a look at this pause. What on earth would cause that pause? Why was the client, this is the receiver of the data. I'll just call it the client. The receiver of the data is getting all this stuff coming in. He pauses 20 milliseconds, and then boom, he sends off this acknowledgement. Starting to. All right, let's see what's going on here. So first of all, if I'm going to go ahead and add a column up here to my profile here. This is already in another profile. I just don't want to do this to you. Just jump around profiles. I'm just going to build this out as we're talking. And in fact, I'm going to minimize data, window size. All right. So window size. Receive window. So notice this number here. In one direction, with the 1514s, I got 65,160. The one who's sending the data, he's saying, I can receive 65,160 at once. That much data can be outlying in the pipe. You can send that much to me at once, and I'll go ahead and start my acknowledgments. Now, the thing is, though, is that this server's not the one receiving, right? Dot one is sending. The big packets are coming from dot one. They're not coming from dot two. So dot one can advertise any window size that he wants to advertise, but he's not the one doing the receiving here. So 65,160, that number, just look at this number here. It doesn't change. He's not receiving data. He's sending stuff. Now in the opposite direction though, you notice that this number is changing. In fact, yeah, you got a question. Correct. The question was, I mentioned that they're not using window scaling. Would that be a consideration if they were using window scaling? For sure. Yeah, absolutely. And I'd be able to tell because a lot of times what you'll see, if you miss a handshake, a lot of times you'll notice like a number. Let me just take a look at the dot twos. These are the empty acts coming back for this data. All right? Look at these empties. In fact, I'm just going to say, I don't even care about the packets with the data. I just want to see the ones coming from 192.168.1.2. Bam. All right. Okay, so these are just the acts. all right? Just the ACKs coming from the server that I'm sending the data to. Now, a lot of times I can tell if I got a window scale or not based off this number. A lot of times the number will be smaller. It'll be something like I showed you, like a 64 or 120, I don't know. It'll be a real small number that doesn't make a whole lot of sense. That's how I can usually tell. That number was scaled, I just don't know what the scale factor is. However, here I'm getting a full size one. It might be scaled, might not. But this is how I know for sure. So 65,535, the receiver of the data is saying, hey, you can send me 65,535 at once. I'll be cool with it. That's how much you can send. That's my receive bucket for the water that's coming at me. It's sending these ACKs. It's saying, great, keep sending. I'm good. Keep your eye here on the window size value. I'm good, man. Rock and roll. Whoa. This number changes. In fact, this number, as we're going forward with our acknowledgments, this number is starting to, where are you number? Here, this number. Notice how it's starting to go down? This number, that receive window, is starting to fill. Now think about it in terms, I'm a receiver, data's coming at me, water is coming down the pipe, I've got a bucket that's catching that, and I'm hopefully dumping the water out as fast as it's coming into my little application over here. Like, here you go, here you go. Now, in this case, the application is going to come in and basically take the water out and do its thing with it. TCP is sitting there, water's coming in. We're starting to fill. Okay. 65,535 is what I usually could do, but right now we're starting to get a little bit of pooling on the bottom. 64,915, that's all you can send now, because it's more's coming in. 61,995, 59,75, 56, that's what's left over. That's how much space I have left in that bucket. So that this receive bucket on the receive side is starting to fill. That's why that receive number, that window, that number is going down. Now, why is it filling? Because the app on the receiving side isn't coming in and grabbing that stuff and taking it home. All right? So this number is going down. So the server that's sending the data can only send so much. He is now limited by that number outstanding. So he sends a bunch of stuff. Now keep in mind, there's no latency between these two boxes. It was like in the, I don't know, I would almost say it's in the nanoseconds. Very, 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 very small amount of, or microseconds, sure. Anyways, this comes down, boom, 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 all the way, look at our window. We come down to 2299. All right, let me remove my filter. So now we have this window size. So this number is dropping 2 big packets. And if you subtract the actual amount of data that's sent, these big packets have 1460 in them. So 1460, 1460, if you subtract these two, that amount of data from my sequence number, you're gonna notice that my window size, you're gonna notice my window size is dropping exactly by that number. In fact, we get down to 2299. That is the client saying, hey server, this bucket's full. I got 2299. That's it. That's all you can send. So the server, on his side, he's dealing with full-size MSS values. You notice he just says he sends one more 1514, just one more packet. That's packet number 139 there. He sends one more 1514. Look, that's all that'll fit. I realize you have a marginal amount of data in there, but you know what? I've already segmented this stuff up. I'm dealing with full packets here, trying to be efficient. There's one more. You can't receive another full-size packet. I'll stop. Your bucket's full. Client. He's got to wait until that bucket clears by the application. Packet number 139 or 140. This guy right here. Packet 140, bam, right here. This is the ACK. Look at his window size. 65,535. So now the receiver of the data is saying, hey, I got an empty bucket now. Layer 7 came in here, took it all out. Let's rock and roll. That took 20 milliseconds. There was that pause. Now that could be the amount of time that it's taking the app to come in and clear that window. We'll start digging. But that, in this case, that 20 milliseconds was on the client side. Why? Because it's receive window filled. Now it didn't go all the way to 0. That's a TCP 0 window. Had it gone all the way to 0, we would see Wireshark indicating some things. I have some traces of that. But basically, whoa, you got a 0 window. That means stop sending. 0 window, I cannot receive anymore. Why? My bucket's full. And TCP is going, I can't do much else until that guy comes and gets it, so no more water. Okay? Question? Good thinking. This is not a window update. Because actually, that's a flag by Wireshark. So Wireshark could have, or should it have? This is a full window again. It's not just a marginal window update. Usually you see that if I sent like let's imagine that I sent like a 30K. And then right after that I send like a 65,535. That one will usually be tagged as a window update. I have some traces that show you that. Why this one doesn't, it must be just because once it returns to a full, the rule for showing that alert isn't triggered. Why? Developer den. I don't know.
For it to be a window update, it cannot acknowledge any new data.
There we go, that's true.
It acknowledges a new segment of data.
I forgot. You're right. If it's acknowledging new data, it's not going to be a window update. It has to be basically an empty ACK. It's like ACK and then one right after it that's empty and not acknowledging new data. That would be your true window update. Thank you. Thank you. All right, so what happens next? We got a full window. Receive window got emptied out. Bucket's clear. Data comes in from server. Bam, 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 bam. Big packet. All right, now again, keep your eye on anything coming from .2. All right, in fact, I'm going to set that display filter again. All right, so here we are, 155. Here's our receive window. I'm sorry, source is .2. There we go. Okay, so we went down to very small, not 0. And now we're wide open again. We're accepting new data coming in, coming in, coming in. Coming in, look at our window size. When does our bucket start to fill? Whoa. Whoa, hang on here. All the way down to here. There's our window update. So 1459, so this is 1 byte less than my MSS. This will cause the server to pause. This time it pauses 14 milliseconds, and then it starts to send its data again. So we're gonna start to see a pattern here. As I scroll, large window drops down to a small number. There was actually one more data packet after this one that we have filtered out. 19 milliseconds await, then we send again. Right, so we're fire hosing data when we can, but the client is hanging us up because its receive window is filling. All right, every time we see the receive window drop to less than the MSS, we see that delay. So right now, is this a network problem? Would upgrading these links from 1 gig to 10 gig do anything? Is this a sending problem? What's the issue here? App on server side's not coming in and cleaning out that TCP buffer fast enough. Now for me, this is where we'll get in, we'll look at a few of the nerd knobs on the receive side within the app, see if we can get in there and tweak anything to go in there and clear it out faster. In this case, they actually, I think they moved to a different backup method that used TCP windows that were much larger and more efficiently. But in this case, the hang-up was on that receiver. It simply could not, the app was not taking full advantage of both windows and the pipe between them. Question?
So just so I understand, the mosquitoes receive column is representing the 192.1.1.
This is the senders, so whoever sent this, 1.2 is getting the data, and he's just saying, my bucket's empty, and boy, it's filling. It's filling, it's filling. Whoa, 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 hang on. I only got room for one more MSS. Stop! Because I don't want anything to spill out. Right. So now, I mean, I do have a couple options here, and we have done this in the past. What if I just gave the receiver a bigger bucket? Right? Enable window scaling, put a multiplication factor on that. That's one option. Probably get things to go a little faster because he's got a big bucket, but the root cause, if I give him a bigger bucket, it might take a little bit longer, but I'm still not seeing app guy come in here and get that water out. If I give him a twice as big bucket, it's good for a while, but then, boy, it starts to fill. So root cause, I need to get in there, and that app needs to scoop that data out faster. Now, for me, that's where I say, all right, that's our problem. We'll dig in to see if we can find any tweaks and things that we can adjust. But a lot of times, it involves involving the vendor, and they got to get in there with their code and figure that one out. But we absolutely isolated root cause. We have a question.
Does this show on the graph?
Oh yeah, I was just about to show you that. Okay, so now that we understand, I don't like to just throw like a TCP trace graph out there until we understand what it's doing. So that's what we just built to, okay? Let me pull up. There's a handy little graph. Statistics. Let me come to TCP stream graphs. Let me go to time sequence TCP trace. All right. Now what I want to see, my goal, is I want to see a nice straight line. My x-axis is time, right? There's my 800 milliseconds of trace file. The y-axis is sequence number. So that's, remember, each byte has an associated sequence number. So what I want to see is a nice, flat, boom line that goes as steeply as possible up and to the right. That means I'm moving data, there's no pauses, there's nothing hung up on either end, data's moving efficiently. But as soon as you see this stepping, that means that something's pausing. One side or the other, we have a wait. Then it's up for you and I to dig in there and figure out what that wait is. Now, a nice thing about TCP Trace, let me just zoom in here a little bit here. Go to zoom. I'm just going to get this guy right there. Okay. Okay, so you can't see it. Well, you might be able to see it from down there, but each one of these little guys here is a packet. Go. There's a little brown line underneath this row of packets here, and that represents acknowledgments, or what has been acknowledged. Okay, let me dig in a little further. All right, so that brown line you see on the bottom, that represents what has the receiver actually act. Okay, so as I see these guys go up, what I want to see is that brown line should come up and meet those packets, all right? It just means, yep, that's been act, and as you notice, if I go up and to the right, you see acts are coming in, okay? 2 more packets. Usually you see 2 more packets, ack. You know, a couple packets coming in, ack. All right, the acts are keeping up just fine. Now, let me back up from here. There's another line. See this line up above me? This is the receiver's receive window. My goal is I always want to have space between the packets and that green line. Ideally, those never meet. But this is a good trace file to show you. Remember the behavior. What happened here is not too far into my packet stream, you notice my receive window, it's coming up, it's keeping in step with incoming data. if we measured that, that's exactly 65,535. That's the space between where the packet is and where that line hits. That's exactly 65,535, and it's going up like this. And then at one point, it freezes, right? And then it goes straight. Notice that? Now the amount of space between my data and that window is closing. The two are starting to meet. That window is filling. It's stuck. As soon as my packets meet that window, pause. That's what causes this 20 millisecond pause. Let me zoom out a little bit, right? That pause is there is because I ran out of the green line. I didn't have any space between the data coming in and that green line, so it pauses. I have to wait until that green line goes up. Notice, as soon as that green line goes up, boom, server's like, sweet, boom, data. And then a certain point in, we start to see the receive window freezes, data comes up to meet it. So whenever I have that type of pattern, right, now that you've seen this in the packets, that's why I like to show you first, this is what's happening with that window size, this is what this means. Now we go to the TCP stream graph, hopefully these numbers make a bit more sense. Now when we look at this pattern, you see that green line? It opens, we send data, we stop. It opens, we send data, we stop. It opens, we send data, we stop. So we are limited, those hang-ups, the stepping, is being caused by that receive window filling. Okay? Now, how do we fix this? Again, we got to get into that receiver and figure out why that app isn't coming in and scooping out that data. I wanted to work on this one longer with them and really get to see what was going on within that part of the stack. However, they chose to go with a different backup algorithm, and then this problem went away. Don't you hate it when an upgrade fixes it? You're like, no, 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 what was wrong? Hate that. I mean, it's good that the problem's gone, but no, let's find out which little tweak we could have made to fix it. But anyway, a lot of times for me, what happens, especially when I'm consulting, my customers are just like, just tell me if it's the network or not. Oh, it's not? Okay, done, not us. Send your report. No, I want to know what it is. All right, so that was a receive window problem. Now let's talk about the opposite side. Okay, congestion window, ooh, the mysterious congestion window. Okay, pipe, we've already talked about the receive bucket, outstanding, how much can be sent at once. Once this guy starts to send acknowledgments, then we can continue to have that much outstanding data on the wire. Congestion window. Congestion window is how much can this server actually put out there. Okay? How much can it actually send? Now, the thing about congestion window, unlike the receive window, the congestion window is not advertised. I can't look within the packets and look at the packet headers and go, oh, there's the congestion window. That's how much this guy can send. That's how much this guy can receive. The congestion window is not a number that is advertised by the server. He doesn't come out and say it. What does that mean? We got to figure it out. Okay? Now the goal of the server is to fire hose if it can. It wants to start sending data. However, it doesn't just come out the gate and slam data. This would be a bad idea for the server. Right? Imagine if this is what the server did. If this is like 10 gig attached, and if the server's like, hey Nick, what are you? You're 10 gig? Sweet. Boom. Let's kick 10 gig out on the wire. Just bam, fill this thing. Well, odds are that I'm not 10 gig all the way from server to client. Even if he has this massive receive window, even if the bucket's huge, and the sending bucket, I mean, I can't take this sending bucket and just shove it down this pipe. What if the pipe's like a teeny little pipe, right? So at the beginning of the conversation, if it's a big file transfer, data transfer like we see here, One of the goals of the server is to figure out how much data can we put on the wire before we start running into problems. Okay? Ideally, the server doesn't put so much out there that it hits its head on the ceiling of the network bandwidth, is what I like to call it. Okay? So the congestion window, it's a sender side limit on the amount of data the sender can transmit before receiving acknowledgement from that receiver. The minimum of congestion window or receive window governs data transmission. Okay? So again, going back to our pipe analogy with buckets on each side, if I have a 10-gallon paint pail on this side, that's my congestion window, but the receive window is just 8-ounce glass, I can only send 8 ounces. However, if he's got a 5-gallon bucket that he can receive water, and I've only got 8-ounce glass over here, then I can only send 8 ounces at a time. So whichever one is smaller, that will govern the rate at which I transmit. Now, the thing about a receive window, though, is it doesn't, depending on the TCP algorithm which is in play, which, to be honest with you, in this conversation or in this talk, I don't have time to go over, but I will point you to a very fantastic session that we have right here at SharkFest. Mr. Simon back there, he's going to be doing my TCP, what is it? My TCP ain't your TCP? Go to that session. Because it's all, he goes into the different TCP algorithms, TCP Tahoe, TCP Reno, TCP New Reno, TCP, these methods that TCP uses for ramping up ramping up data, ramping up the rate at which it is sent while still avoiding congestion. So, but to keep it within our context here, congestion window is some multiple of the maximum segment size. All right, so I take my maximum segment size, I do some multiple of that number. That is my congestion window. Now, what do I start at when I'm at the beginning of a conversation? Most stacks will do the slow start method. So initial size will vary. It just depends on the algorithm that's in play. It could be 1, 2, 4, 8 times the maximum segment size. What does that mean? It means that if I got a bunch of data to send, I'll send, let's just say, for example, it starts at 2. I send 2 full-size packets. I wait for all that stuff to get to my receiver. Receiver says, great, Chris, thanks. Oh, great. He got two maximum size packets. He got 2 MSSs. Sweet. I'm going to send 4. 1, 2, 3, 4. Wait for all that stuff to get there. He comes back with a couple of ACKs. Awesome. Man, 4 worked. Cool. Didn't hit any thresholds. I didn't bang my head on the ceiling of bandwidth. Let's send 8. Bam, 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 bam. All those 8 get over to him. He starts to acknowledge. So the server will do something called slow start. It starts to send data, and then it will double that number of maximum segment sizes until it hits an internal threshold, slow start threshold. At that point, and that's another number that we can talk a little bit about, but he hits that number, and then he just marginally starts to increment the amount of data he sends. Now the catch with all of this, guys, is that the server never advertises what that number is. It's also not a fixed number. It's a number in motion. The idea is that we send as much as we can, as efficiently as we can, without hitting our head on bandwidth or retransmissions or causing network congestion from our own traffic. TCP wants to figure out what's that float point where I can send data without retransmissions and still make use of your receive window. So TCP is smart. Right here, the server is saying, like, hey, self, I'm going to start sending slow until I figure out how much this network can take. I'm just not going to tell anybody how much that is. We got to figure that out from the trace itself. So let's go ahead and see this in play. All right? Enough PowerPoint. How much time do I have? Whoa, man, we just have so much fun here. Okay, I'm just going to do this one, and then I'd like to show you guys some more case studies. There's some pretty interesting things. Okay, so first thing I'm going to do, here's just a slow start good, okay? I'm going to take a look at our network round trip time, 90 milliseconds, okay? Where'd I get that from? There's my round trip between the SYN and SYN-ACK. Three-way handshake. I send a GET to that server, okay? 92 milliseconds later, server comes back, it sends me a couple of packets. I see an ACK, then this is where you're gonna start to see slow start do its thing, okay? When we're actually beginning to send data out. So here we go. So we have actually, this first one, okay, there was a GET and just a 2-packet response. That's why we didn't see anything else go. This next GET, this is a GET from the client to the server. This time the server has more to send. This is an actual OK. It's not a 404 not found. This is a real file that I'm going to send across to you. You notice how many full-size packets the server sends? We have 1, 2, 3. It starts to see an ACK come in. We still have some room in our receive window over there on the receive side. Great. The server paused, right? It didn't want to send any more than just the minimum number of frames or just that getting started number of frames. So it waits that 90 millisecond, in this case 93 millisecond round trip time, and then it sends 1, 2, 3, 4 pauses. Okay, it waits for, probably waits for this ACK to come in. Then we start to see the number increase, 1, 2, 3, 4, or it actually put out there a couple of times. Waits another round trip. Now we start to see the congestion window go up. 1, 2, 3, 4, 5, 6, 7 full-size packets. Waits to get some of those acknowledgments. Keep in mind these acknowledgments are in flight, okay? So it starts to receive those. We're capturing client side. This time, how many big packets we see? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're starting to increase the number of full-size packets we put out there on the wire. The reason, we're slow starting the congestion window. And you can see this if you come into TCP Stream Graphs, TCP Trace. This is a nice, clean example of slow start, right? So it starts small. Let me put a couple segments out here. All right, just one. Let's add a couple. Let's add a couple. Let's add a couple. Let's go, 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 go. Now, ideally, I never hit my green line. That's my receive window. You see the space that we maintain between the data and the green line? I got space. So if I had a hang up here, it's not the fault of the receiver. In fact, you see our stepping. What do you think that's caused by? Every one of those lines is a consistent number, isn't it? You see how those lines are all about the same, right? So if anything, let's check that out real quick. Now this wasn't a very large trace file or long transfer, so we don't see a ton of them, but let me minimize this. Cool thing about TCP Trace, oh, come on now. All right, I'm just gonna move this out to the side. Cool thing about TCP Trace is you can click at any point on this graph, and you can look right next door and see where the delays are. So if I take a look at, here, let me look at this delay. All right, so I clicked just before the delay point. I see that 91 milliseconds. If I click on the next step, there's my 100. So that's just my network round trip time. All right, but it's doing slow start. So, and again, there wasn't a ton of data, but the idea is I just want to see this guy go boom to the sky. I just didn't have enough data to see it actually go much higher than past the slow start. Now at some point though, what we are going to see, whoa, I'm going to lose my mic is what's going to happen. All right, now at some point here, you notice that we start to see about the same amount of data. You see the number of packets that's going out there is starting to look consistent, right? You see all these little, I got my pause point, but then you see like this line right here, this line right here, this line right here, this line right here. So it looks like I hit my internal slow start threshold. That's the amount that the sender is going to be rate limited to. It's rate limiting itself. Why? I'd have to dig into the TCP stack itself and figure out what it's doing. But basically, it's limiting itself. It doesn't want to use more than a certain amount, okay? Now, if this kept going and I was always seeing this, then it means that my congestion window isn't increasing. Or it's also possible that the application on that side just is not handing the TCP stack enough data to then send more data or more water down the pipe. It's got a big bucket on that side, but there's just no water in it, right? In fact, yesterday, I'm trying to build to a trace file that I was given yesterday by Randall. There's a gentleman in the audience over there that we were sitting and talking and doing some troubleshooting on one of his systems, and we actually ran into that issue, so hopefully I can show that. So, okay, so point that I wanted you to take away from this, 2 types of windows, receive window, congestion window. Congestion window is the scary nebulous one, this number that's set within that server. It does slow start, then it goes into congestion avoidance. The goal is it doesn't want to overwhelm the network. It has no idea what is going on between both endpoints. So it does a slow start, and then it will eventually slow itself down to where it's sending at a threshold as long as I don't hit retransmissions. Now, if the sender, if that server hits retransmissions, let's just say it slams data, we start to see some retransmissions. Whoa, okay, or some dupbacks coming in. It's going to need to resend data. What that will do to the congestion window on the server side is it's going to say, look, I hit my head against the network. I hit my head against the throughput or bandwidth that I have available to me. I'm going to reduce my congestion window. I was too aggressive. So let me reduce the amount that I'm putting out there on the wire. Okay? That's what it'll do because it wants to avoid congestion if it can. All right. So takeaway points again. Let me bring up my Prezzo. Okay. Let me now show you a couple of interesting things that I've seen out there. One is, TCP Delta. Oh, I gotta talk to you about that first. Okay. Now there's, in my profile here, we talked about this when I first started up my Wireshark, is I have 3 timers. I like it that way with my TCP plane profile. A running total, right? Delta time. But then I have this TCP, it's a TCP delta. Now what's the difference? Now some people have told me, okay, they just bring up their trace files and they're looking for delays, looking for pauses, looking for things that hang up. So they bring up a trace file with lots of different conversations in it. Then they come over here and they sort on the delta time. Okay, we sort on delta. Let's go down to the bottom. According to the delta time, my biggest pause, quote unquote, in this trace file is 423 milliseconds. That's the most amount of time between packets that I have in this trace file. 423. But think about it. I already told you, I mean, look at all the green lines you have going here. I already told you there's lots of different conversations happening in this trace file. There's lots of different parallel TCP connections. So this number is just telling me for the entire trace, I only have, this is my largest amount of time space that I have between packets. Is that a useful number to me at this point? Is that where my pause is? Is that where the delay is? I've been looking for this delay. That's a tough number to use. Why? Because I don't know that the number that, the packet that came above this had anything to do with the conversation that that packet is a part of. Does that make sense? Follow TCP stream. Someone just said, go ahead and follow the TCP stream. Okay, I could do that. Let's do that. I'm just going to come down here, say follow, and I mostly agree with you. I want to isolate the conversation, but I don't want to extract the data. I just want to see the timers. So I'm going to go to conversation filter, TCP. And then I'm going to resort my numbers. Okay, so what was of 427 or something. Now that this conversation is in context with itself, that just became 611, okay? So in context now, I have a single thread and I can see those delays. But if I'm dealing with a in this trace file, this was between a web front end and a back end database. You've got tons of connections. I'm looking for slow ones. I don't want to see just delta time sorted, and guess what? I certainly don't want to have to do follow TCP stream or set a conversation filter on every single one to then go and sort the delta time column. Everyone agree? That's a lot of manual stuff. So what I'd rather do, I want to sort on time since previous frame in this TCP stream. Now, this number, let me jump to the bottom here. This number tells me not delta between this packet and the one previous to it that is in the capture. This tells me the amount of time between packets in that stream. So now I don't have to filter it. Now I can go looking for my pauses and my delays. If you do this, first let me show you how to do it. Let me make sure, because I don't recall if that's a default setting yet. If you open up any TCP packet that you have and come down, and do you have TCP timestamps? Okay? Not the option timestamps. This is actual timers that Wireshark will show you. If you don't have this at the bottom of any TCP header, if you do not see timestamps, then what you need to do, just right-click the TCP header, right-click that guy, come over to Protocol Preferences, and calculate conversation timestamps. Okay? If you don't have that, do it. Why? Because that's a really great column. Activate those timestamps in your TCP. That's in your TCP preferences. Now, I can come down to, let me pick, oops. Did I accidentally uncheck it? I might have unchecked it. Oops. Okay. Now I got my timestamps back. All right, cool. So now I can just pick any TCP packet. I can come down to timestamps, and I want to create a column time since previous frame in this TCP stream. Right-click, apply as column. Now I have a column that will give me context-based pauses in my TCP streams. Okay, so now I don't have to go filter them all. Now I can just sort on that column. And I can come, let me jump down to the bottom here. Let me show you which ones to ignore. Or actually, you might be able to tell me. First of all, I got some resets up there, right? So this just tells me 130 seconds in, 125 to 130 seconds into some of these connections, they were being reset. Seems like they were just idle too long, right? Or one side or the other was like, hey, let's reset. Boom, shut it down, hang up the phone. After that, we have some keep alives. After that, we have a few acknowledgements. You're going to hit a big window, or actually see the blue lines here. In my profile, I paint my fins blue. Again, my way or the highway, right? I see a bunch of 60-second TCP keep alives. So you're going to see a bunch of stuff. If you just take just a standard right off the wire trace and you sort on this column, you're going to see stuff like this. Look for numbers that are on these boundaries: 45 seconds, 60 seconds. You just saw it, 130. Right? Those could be timers like keep alives, fins. It could be timeouts. It could be stuff like that. What I look for, let me show you specifically where my eye goes. What I want to see is let me scroll down to it. I'm a scroller, sorry. Laura's not here. Haha. Don't tell her. Okay. The type of thing that I'm interested in looking at, you notice here it says get. Again, I'm sorted on my time column. Notice here that this says get, request, get. That 30 seconds was just the client, it could have been the client just waiting to do something. Client think time, right? The client was the one, 30 seconds ago it did something, 30 seconds into this stream it then sent a GET. I'm not going to focus a ton of attention on that at this time, unless I start doing some sorting and filtering. The complaint in this thread that I was sent was that an alert was being sent by Oracle that it was taking too long to hear back from reads. There was a request sent to the server and it was taking way too long to hear back from the database. So I'm not as much interested in the request, okay? What I want to see is, where are we? Response. When I see 24 seconds and it's a response, that's one that I might want to come and say, okay, let's filter. Let me go to my conversation filter. Let's put this guy in context. I'm going to come over here to my frame number and resort. All right. Sin, Synac, GAC, wow, we're in the microseconds. Okay, Sin, Synac came back, microseconds. We see a TNS request. That's request data, happens pretty fast. ACK coming back, boom, 24 full seconds, and that's when I see a response. That's exactly what the client was complaining about. So we're able to go in and see exactly which request it was. We're able to set a few filters and saying, does this happen all the time? Is it just sporadic? But the way that, for me, I initially found it, I know that seemed like a blurring column, right? With all the different, 90 seconds, 130 seconds, that kind of stuff. But you'll start to get a feel for what you can overlook. All right? And for me, I'm always looking for, in that column, if I ever have a huge trace file and I just sort it, I'm looking for responses, HTTP 200s, any type of response from a server, because that means that that delay was server side. All right, so the actual application was taking that long to respond. I got one more case file I'd like to show you before we wrap, coming up on 2:30. So hopefully this is all helpful to you guys, and you can just see some of my tricks for analyzing TCP. Okay, the next one. I had a problem where let me see here. Okay. Problem where a client was trying to access, okay, client brings up his little file explorer. He's trying to access a certain file on an LDAP server, couldn't access it, couldn't get to it for about, I don't know, 20 to 30 seconds or so. If he sits there and waited long enough, his file begins to transfer and he can actually pull the file down. But there was that 20 to 30 second pause, and it happened every time they went to try to access a new file. All right? This is the trace file. Now, if we take a look at the Synac right away, your eyes over here, 86 milliseconds of round trip time. If I come here to the Syn, and I go down to, oops, let me bring up my little headers here. If I come down to the IP header, my time to live on the Syn is 128. All right? That means that I am capturing this Syn before it is routed. This is a full time to live on the IP header. We get a response from the server, 122, unless something's messing with that in the middle, which is possible. That server's probably 6 hops away. The final packet of handshake, there's my acknowledgement going back to the server. After that, I actually the client sends its 404 bytes to the LDAP server, search request. Then something weird happens. I get a response from the server. It has data in it. This packet is 563 bytes. Okay, in fact, I'm actually going to come in here and just do my TCP segment length. Right click, apply as column. So now we have the actual segment length that was in the packet. In fact, right now that's more valuable to me than just overall packet length. Okay, segment length. So the actual amount of encapsulated data within the packet. I'm going to remove window size for now. All right, and tell you what, this one too, I don't need it right now. All right, so send my request, I get a packet back. Wireshark says, whoa, 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 buddy. TCP previous segment not captured. This is the first packet that I got back from the server. Send my request. Okay, let me back up to my request. If I come into this packet, I'm looking at my sequence number. The requester, the client here, is saying, hey, search request. I'm starting on sequence number 1. My next expected sequence number will be 351. When he responds in his ACK, the ACK part of his header value should be 351. So let me take a look at this packet coming back from the server. 351, sweet, he got my request. It got there. But look at his starting sequence number. This is the first packet that I'm receiving from the server. He's beginning on 1461. Whoa, 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 hang on. A packet above, I just send him, we were sequenced at 1, right? The handshake did that. That's that ghost byte that we sent. We start at 1. He's telling me he begins at 1461. What does that sound like? What did he send? Before the one that he's on, how much space is that one? The 563, okay? Before this 563, he had a full byte packet, or full MSS packet that he sent, 1460. I never got that one, but I got the residual one. Okay, that's packet 5. Client says, okay, DUPAC. If I look in that DUPAC and in the options and everything, the way SAC works, the client says, actually, let's look at it. It's a good opportunity to learn a little bit about SAC. Client says, okay, right. I'm going to ACK 1 because that's where we were. I'm good to 1, to where our handshakes were. However, if I open up the options and I come down here to TCP option, SAC, selective acknowledgement, left edge is 1461, right edge is 2024. That's ACKing the smaller packet. So the one that I'm missing is the delta between where I'm good to and the left edge. I'm good to 1, and I'm missing between 1 and 1461, that MSS right there. So hey server, that's the packet I want. But I got this little residual one you sent, this 500 byte thing. We're good there, don't resend that. Then what happens? I don't hear anything for 21 seconds. Sound kind of like what the guy was complaining about? Our goal is always to take what we hear, the symptoms of what we hear, and match them to our packets. He said he was waiting 20 seconds to begin a file transfer. There it is. But what caused this? Well, notice the size of packets that I see coming in. 536. Okay. Interesting. Right away, I'm going 21 seconds. That server is doing other things on the other side. From the client perspective, I don't have enough information. Let's go server side. So we captured server side. Let me get that trace up for you. And check out what this guy was doing on this server side. Okay? Ignore this red for now. Okay. SYNAC, ACK, search request. Okay? Got the packet in from the client. Server sends a 1460. I sent my 1460 and my 563. Everyone with me? We were just capturing now from the server side. So that 1460, I send it out there, I send the 563, and then I get this 93 milliseconds later, I get this DUPAC saying, hey, I missed the 1460. Server says, okay. You see the 2.95 seconds on packet number 8? Server goes, that's my retransmission timer. We haven't done a whole lot of talking yet, so I'm going to wait almost 3 seconds to retransmit this. That's my retransmission timer at the time. How come I didn't do a fast retransmission? What triggers a fast retransmission? Triple dupe. I got to get 3 dupacks. And then that'll trigger a fast retrans. I didn't send enough data to get 3 acks. So I have to wait the full TCP retransmission, which at this time is 3 seconds. I haven't even started slow start. I haven't done anything else. So I'm at the very beginning, that horrible 3-second retransmission timer, which happens at the beginning of a TCP conversation. Worst time to have packet loss. So server sends packet 8, 3 seconds. Here's the big one. Nothing. Server didn't get anything back. It doubles the retransmission timer, packet 9. Sends 6, or 6 seconds later. Here's another big packet. Gets nothing. 12 seconds. Let's try this, because man, that client is not responding. I'm sending this big packet. Finally, server says, you know, okay, packet 10. These big ones aren't working. So you know what I'm going to do? The stack has the option of giving the minimum, when in doubt, MSS a shot. You see that 536 on packet 10? 536, if in our TCP header, or in our TCP SYN-SYNAC, in our handshake, if we did not exchange an MSS, if MSS was not there, the minimum MSS that will be assumed is 536. So, server says, you know, these big ones aren't working. Last ditch effort, I'm just going to give this a shot. 536, bam, ACK comes back. Oh, whoa. So it took the same data, but it just sent it in smaller chunks. And notice, look at that TCP segment length. Watch this. We never see it recover. It never goes bigger. So now the MSS internally on the server side is this 536. We never try again. Now what happened? Okay, well check this out. Look at the MSS. Look at the MSS on the SYN. As it comes in, the MSS says 1460. This is on the SYN, right? The server sends SYNAC 1460. There's our MSS, right? Let's see what the client received. Remember, 1460, 1460, client side. Again, SYN, MSS, 1460. That's the biggest I can receive, Mr. Server. 1460 actually got to the server. Server turns around, 1460. We receive the SYNAC, 1432. He let it go at 1460. I receive it at 1432. What happened? Something along the way. His gateway actually reached up into that TCP SYN and said, oh no, we're gonna ratchet that down a little bit because I've got all this other stuff, this WAN acceleration, I got some things, I need some space. Because 1460 doesn't give me any room in the TCP headers to do any other fun stuff. It's a full payload. 1460, if you add a 20-byte TCP header, that's 1480. A 20-byte IP header, that's 1500. You just hit your MTU. Server thinks 1460 is legit, right? Client goes, oh, 1432, okay. Cool, that's all you can receive? Good, that's all I'll send. So one side thinks we can send bigger than the other. Cool. Server was on the wrong side of that deal. So this 21 seconds is the server going, okay, these large ones aren't working, let's try a small one. And because it was so early in the TCP stream, it didn't give the server enough time to reduce its retransmission timer, because it didn't even enter slow start. So that retransmission timer would have gone from 3 seconds to way less once data started to actually move. So what do? Well, the outbound router on the client side had recently been replaced. And whoopsie, they forgot to have that router. It's a command on common firewalls. You can actually reset the TCP MSS at the router level if you know you have stuff between that you have to handle. Things like WAN acceleration, things like other boxes that muck with stuff in the middle. The router itself was going up and saying, TCP MSS, let's kick that down to 1432. Give some room for some header room for this other stuff. So we went on that router, the outbound router, adjusted that, and by the time this MSS, or this SYN rather, the first SYN from the client lets it go at 1460, the router fixes it to 1432. By the time it arrives at the server goes, oh, 1432, cool. 1432, let's just do that. It's not negotiated, but each side can agree, like, oh, sure, all right, that works. Even if he sent a 1460 the other way, it's still getting sent down to 1432. So they both won't go to that upper limit of packet size. Once that happened, 1432 was the MSS. We had enough sealing in the middle to get through the other stuff it had to do, and then we were good to go. All right, guys, this was just one thing that I've run into. Got a lot of traces and a lot of fun stuff to work through, but time has run out. So I had a great time today. I hope you guys did, found something useful. If you have any questions, please come up to me. I'll be around for the rest of Shark Fest. I'd really like to get to know and meet more of you guys, so please come up, let's chat, and thanks for coming.